Chapter 7, Coherence and Consistency. We'll start out by talking about bus-based coherence, then compare and validate and update coherence protocols, and we'll finish up by talking about memory consistency. Several configurations are possible for a memory system. First of all, there's the shared cache, which is popular in chip multiprocessors such as the Power 4, Spark, Pentium, and Itanium. Then there is a bus-based shared memory where all of the processors are on one side of the bus and memory is logically, anyway, on the other side of the bus, so that memory references need to traverse the bus to get from processor to memory. Then there is a dance hall arrangement where you have an interconnection network between the processors and the memories. This is no longer popular because all of the memory is uniformly far away. The last is a distributed memory, which is a popular way to build larger size systems. Now I have one question before we go away from this slide. What kind of organization represents a NUMA multiprocessor? A bus-based symmetric multiprocessor builds on two characteristics of uniprocessor systems: the existence of a bus over which transactions to memory take place, and the fact that a finite state machine describes the behavior of each cache line. For example, when a line is read in from main memory, the cache transitions to the clean state, which is sometimes called valid. When the line is written, it transitions to the dirty state. A bus transaction takes place in three steps. First, the device that desires to transfer information arbitrates to acquire the bus. Then it specifies what action it wants to perform at a particular address, for example, read or write, and then it transfers the data. When a transaction goes out on the bus, it is visible to all devices. But most devices ignore it. Only the responsible device carries out the transaction. For example, if the memory word is to be written, only the memory that contains the word will take action pursuant to the bus transaction. If a cache in a uniprocessor is write-through, a line can be either valid or invalid. This is true, by the way, regardless of whether a cache line is allocated on a write-miss. If a cache is write-back, not only the valid and invalid states exist, but also the dirty state, which indicates that at least one word in the line has been modified since being read in. Multiprocessor caches work in the same basic way, with extensions to keep memory coherent. In small multiprocessors, a concept known as snoop-based coherence is usually used. This means that each processor's snooper pays attention to all transactions on the bus and may change state even when a transaction is destined for some other processor. For example, if another processor writes a line that this processor's cache is holding, its copy of the line is no longer up to date, so it may have to invalidate it. In a coherence protocol, both caches and memory take actions as transactions go across the bus. The cache controller updates the state of the relevant cache line, returns data when it has a valid copy, and may generate another bus transaction in response to a transaction that it has received. When a read or a write request is made to main memory, the memory controller needs to respond to these requests. When coherence transactions like state changes or invalidations occur, they apply to a whole cache line, just like transfers from main memory to and from the cache are done a line at a time.